Imagine walking towards a wall. You can get closer and closer without ever actually touching it. Limits in math are similar. They help us understand what happens to a function as its input approaches a specific value, even if it never actually reaches it. Think of a curve on a graph. Sometimes there might be a hole in the curve. Limits help us see what's happening to the curve as it gets infinitely close to that hole, even if we can't calculate the value at the hole itself. Limits are essential in calculus. They form the foundation for understanding continuity, derivatives, and integrals, which are crucial for describing change in motion. This exploration into the world of limits will equip you with the knowledge to tackle these mathematical concepts head-on. Mathematicians use a specific notation to represent limits. It might seem a bit strange at first, but it's actually quite simple. A limit is written like this. Lim as x approaches a of fx equals L. Let's break it down. Lim stands for limit. X approaches a means as x approaches the value a. Fx represents the function we're interested in. L is the limit, the value that fx approaches as x gets closer and closer to a. So this notation tells us what value the function approaches as its input approaches a certain point. It's like a mathematical code that helps us understand the behavior of functions near specific values. The simplest way to find a limit is to substitute the value that x approaches directly into the function. For example, let's say we have the function fx equals x squared, and we want to find the limit as x approaches 2 lim as x approaches 2 of x squared equals. We can simply substitute x equals 2 into the function, 2 squared equals 4. Therefore, the limit of x squared as x approaches 2 is 4. This method, known as direct substitution, works when the function is well behaved and doesn't have any jumps or holes at the point we're interested in. Direct substitution isn't always enough. Sometimes we encounter functions that become undefined at the point where we're trying to find the limit. For example, consider the function fx equals x squared minus 1 over x minus 1. If we try to find the limit as x approaches 1 using direct substitution, we run into a problem. The denominator becomes 0, and division by 0 is undefined. In such cases, we can often simplify the function first. We can factor the numerator fx equals x plus 1 times x minus 1 over x minus 1. Now we can cancel out the x minus 1 terms. This simplification allows us to use direct substitution lim as x approaches 1 of x plus 1 equals 1 plus 1 equals 2. So even though the original function was undefined at x equals 1, the limit as x approaches 1 exists, and is equal to 2. In this section, we'll be dealing with radicals and how to rationalize for clarity. Limits involving radicals, such as square roots and cube roots, can pose some challenges. Consider the function f of x equals the square root of x minus 2 divided by x minus 4. If we try direct substitution to find the limit as x approaches 4, we get 0 over 0, which is undefined. To resolve this, we can use a technique called rationalization. We multiply both the numerator and the denominator by the conjugate of the numerator. This means we multiply by the square root of x plus 2 over the square root of x plus 2. This simplifies 2x minus 4 divided by x minus 4 times the square root of x plus 2. We can cancel out x minus 4, and now direct substitution works. So the limit as x approaches 4 is 1 over the square root of x plus 2, which simplifies to 1 over the square root of 4 plus 2, giving us 1 over 4. Therefore the limit exists and is equal to 1/4. Section 6. The conjugate approach. Taming unruly expressions. The conjugate approach isn't limited to radicals. It can also be helpful when dealing with complex fractions or expressions with multiple terms in the numerator or denominator. For example, consider the function f of x, which equals 1 divided by x plus 2 minus 1 divided by 2 all over x. We can't use direct substitution here because of the x in the denominator. Instead, we simplify the complex fraction by finding a common denominator. This simplifies to negative x divided by 2x times x plus 2. We can now cancel out the x, resulting in negative 1 divided by 2 times x plus 2. Now, direct substitution is possible. The limit as x approaches 0 is negative 1 divided by 2 times 0 plus 2, which equals negative 1/4. By using the conjugate approach, we've successfully navigated a seemingly complex limit problem. Section 7. Common errors and how to avoid them. Even with these techniques, it's easy to make mistakes when calculating limits. Here are some common pitfalls to watch out for. First, assuming the limit doesn't exist. Just because direct substitution doesn't work doesn't mean the limit doesn't exist. Always try simplifying or using other techniques before concluding that the limit is undefined. Second, incorrect algebraic manipulation. Be careful when factoring, simplifying, and rationalizing. Small errors can lead to incorrect results, so double-check your work to avoid these missteps. Third, ignoring restrictions on the domain. Remember that some functions have restrictions on their domains. For example, you can't take the square root of a negative number. Always consider the domain of the function when evaluating limits. By being aware of these common errors and practicing your algebraic skills, you can improve your accuracy and confidence in calculating limits. Section 8. Limits in action, real-world applications. While they might seem abstract, limits have practical applications in various fields. In physics, limits are used to calculate instantaneous velocity and acceleration, crucial concepts in describing motion. In engineering, limits help analyze the behavior of structures under stress and strain, essential for designing safe and reliable buildings and bridges. In economics, limits are used in marginal analysis to determine the optimal production levels and pricing for goods and services. These examples demonstrate that limits are not just mathematical curiosities, they are powerful tools for understanding and modeling real-world phenomena. Section 9, wrapping up, the importance of limits. We've explored the concept of limits, approaching a value without necessarily reaching it. We've learned the notation, mastered techniques like direct substitution, factoring, rationalizing, and using the conjugate, and even uncovered common errors to avoid. Limits are fundamental to calculus and have wide-ranging applications in various fields. They provide a way to analyze functions, understand their behavior, and make predictions about their values even when direct calculation is impossible. As you delve deeper into calculus, a firm grasp of limits will be essential. It will empower you to explore more advanced concepts and appreciate the elegance and power of mathematics in describing the world around us.